So I'd like to now introduce our next speaker, Luke Hecht from the Wild Animal Initiative and Durham University. And he's going to be speaking to us today about optimizing population density for wild animal welfare. So Luke, if you'd like to share your screen. Perfect.
Cool. Yeah, thanks. My name is Luke, and I work for Wild Animal Initiative as a grants manager and researcher. Yesterday, you heard more about our grants program from my colleague, Kelly Forsyth, but I'm here to talk about some of our research related to the potential for improving wild animal welfare through contraception, also known as wildlife fertility control. So fertility control is usually discussed in the context of human-wildlife conflict to replace things like poisoning and hunting, where animals are killed often in an inhumane way. But we think the potential benefits of contraception might extend farther than that to positive impacts, such as through reducing reproduction, allowing for increased maintenance of the body condition of would-be parents, reduced competition among siblings, and also reduced effects of population density among the rest of the population, which will be the focus of my talk today. So that includes like reducing competition and disease transmission. So although I'm generally very optimistic about the potential of wildlife fertility control, I don't want to leave you with the impression that it's a silver bullet. There are still welfare risks associated with current fertility control technologies that require more research. But for the purposes of today, I'll mainly be assuming a hypothetical side effect-free contraception method. So now I'll go into some technical specifics of how we think about the population level welfare impacts of wildlife contraception. So as a population grows towards its maximum sustainable size or its carrying capacity, denoted as K, its growth rate needs to decline from its baseline level to 1, or net zero growth. In a closed population, this stabilization can be achieved by reducing fecundity, the rate of reproduction, or survival, which is effectively how long each individual stays around in the population. Reductions in survival seem most relevant to welfare. For example, a year in which an animal was more likely to starve or be predated or die of disease was probably also a year during which they were more often experiencing hunger or fear or just illness. So I'll also be assuming in the rest of this presentation that age-specific survival is proportional to age-specific welfare. I'll get into that a bit more later. It's definitely not ideal, but I think there's some justification for that. That's a rough proxy. So by limiting adult reproduction from the outset, contraception reduces a population's baseline growth rate, and that reduces the magnitude of reduction in growth rate that's left over for natural density-dependent processes to account for. So it effectively imposes density-dependent fecundity on populations that might otherwise have been stabilized through reductions in survival related to things like starvation. To understand the potential for effective fertility control to improve welfare in a given population, we need to understand at least two main factors. The first is straightforward. It's the extent to which welfare varies with population size. That might be a simple linear decline from a small population to carrying capacity. On the other hand, welfare might be more or less affected at particular levels of population density. For example, a disease that primarily affects juveniles might cross its epidemic threshold, like the R number being greater than 1, at a relatively low population density, producing something like this concave curve. Alternatively, a species life history strategy might cause individuals to delay reproduction when resources are scarce, investing in their own survival, and this strategy might naturally forestall the most severe welfare issues until the population is near its limits, producing something like the convex curve. An exclusive focus on average welfare would likely motivate us to keep wild animal populations small, large enough to satisfy social needs, but small enough to minimize competition and disease. However, in this model, reducing population density may increase average welfare, but it also reduces the number of individuals benefiting from improved conditions. And according to many ethical views, as well as practical considerations such as around conservation and other things, it's likely better to have more animals, assuming they're still living good lives. Therefore, I'll focus on total welfare, essentially the sum of welfare across the population in the remainder of this talk, unless otherwise specified. So if we have that convex curve where average welfare only declines near carrying capacity, a small reduction in population size might actually lead to quite a large increase in both average and total welfare, even with fewer individuals in the population. So this heat map summarizes that in more quantitative terms. So as the density-dependent welfare curve becomes more convex, and the density-dependent declines in welfare become more acute, the scope for increasing total welfare by some specific reduction in population size, in the best case scenario, becomes greater. Here's a more stylized version of that heat map with species speculatively placed on it. The names are in quotes because although I think there's some evidence for placing them in these quadrants, the truly appropriate evidence doesn't exist yet. One species, however, where we have something approaching the necessary information is in wild donkeys. Specifically data from a 1991 paper by Chuckinot. We can potentially use that data to place the donkey on this grid. So Chuckinot 1991 reported demographic rates for two populations, one at its carrying capacity. You can see that at the lower right of the screen here. And one at around half that density with a positive population growth rate. So the lambda about 1.19 indicates that it had a roughly 19% growth rate, which is pretty high. They found that most of the density-dependent decline from that point to the carrying capacity, the lower right, was due to reduced juvenile survival and to individuals beginning to reproduce at a later age. You can see these in red in the lower right. If we assume that age-specific welfare is proportional to age-specific survival, as I mentioned earlier, we can estimate welfare expectancy, which is essentially the expected value of lifetime welfare for a low density population and a high density population. This satisfies the first part of what we need to know, like how density dependent is average welfare, at least insofar as we can trust that assumption that survival and welfare are proportional. But with only two data points, we can't be too sure of the second part, the shape of the density-dependent welfare curve. While we don't have any data points from this paper between 50% of carrying capacity and 100% of carrying capacity, the data given are most consistent with a broadly convex shape of density dependence. So as I mentioned, this paper described two populations, one stable at its carrying capacity and one at around half that density, growing at a pretty high rate of about 19% per year. But this rate is almost the same as similar populations that had recently been reduced much farther below their carrying capacity by severe culling, for example. So like responding to that, rebounding in their population size. And that suggests that there's this sort of more stable line at population sizes below half of their carrying capacity, at least in terms of population growth rate. So if the density-dependent welfare curve is convex, then it's likely that reducing the population density by some moderate amount would lead to positive results in terms of not only average welfare, but also total welfare. So here we modeled on the vertical axis an imposed reduction in fertility of various degrees, with the population naturally stabilizing at a lower size through a compensatory increase in juvenile survival and maturity based on what we know changed between a maximum density population and a lower density population in these donkeys. And that is up to the limit of juvenile survival reported in that lower density donkey population. So we simultaneously varied the shape parameter, that is how convex or concave the relationship is, and the amount of fertility control applied, essentially what proportion of the population is sterilized. We found that the largest potential improvement in total lifetime welfare is expected around a 50% reduction in fertility, given some, well, I guess sort of independent of the shape parameter, that's sort of the best case. But an improvement is expected as long as welfare expectancy has some convex relationship to population density. That is up to a 60% reduction in fertility, beyond which the population is unsustainable. So where does this leave us? I think we can, with modest confidence, place this donkey population about here on the heat map. The assumed age-specific survival welfare relationship implied an approximately 50% maximum reduction in welfare at carrying capacity, corresponding to a welfare density dependence factor, that horizontal axis, of 0.5. And we also inferred from evidence mentioned by the original study's authors that there's probably a convex relationship between welfare and population density. So yeah, in conclusion, it seems like fertility control might be able to preempt more harmful mechanisms of density dependence. And populations for which density-dependent welfare is convex stand to benefit the most from realistic levels of fertility control. But although I think this is one of the stronger examples out there, we would really like to have better welfare indicators to work with and have them corresponding to more discrete levels of population density and stages of population growth, so we can better characterize the curvature of that density-dependent welfare relationship. Yeah, I don't have time to go into detail here, but I do think that survival has a lot recommended as a welfare indicator, at least where we have age-specific survival. So I'm not talking about longevity, but age-specific survival rates in combination with this welfare expectancy idea, which I have a paper about. But it's also a very coarse indicator, only directly capturing the extremes of poor welfare and only poor welfare. Even if the frequency of those is likely to be indicative of more common and survivable challenges. But with better welfare indicators and more studies relating them to population dynamics, perhaps we can fill out this grid on the right and learn more about what species and populations to prioritize for fertility control and other potential welfare interventions affecting demography. Yeah, thank you.
Great, thank you very much, Luke. In the interest of time, we've probably only got time for one question, but there's quite a few in chat, so hopefully you'll be able to answer those afterwards. But this is a question from Roz at the RSPCA. In what circumstances do you think it's desirable or feasible or a priority for people to intervene in natural population control processes and artificially manage wild population sizes through fertility control?
Yeah, I think it's most straightforward if it's already a managed population that's being managed by something like poisoning or hunting. But yeah, yeah, I'd be more confident of it being net positive there, but I would also want more research kind of along the lines of some of what I talked about to figure out how to do it best. Um, in terms of populations that aren't currently managed, uh, yeah, I feel like humans are having an impact on pretty much all populations already. Um, but I would be a lot more cautious in looking at some of these things, like what their social structure is, for example, to make sure that fertility control wouldn't, say, like increase aggression or just cause a complete social collapse.
Great, thank you very much. So hopefully if you've got time to stick around online and respond to some of the questions in chat. And I'll now pass back to Hannah to introduce our next speaker.